Hello everyone, today we are presenting our project titled Hurricane Evacuation Route Planning completed by Jacob Demmons and me myself Rohit Kumar. Our goal was to design an intelligent system that can help to identify safe and efficient evacuation route during hurricane condition. About hurricane evacuation route planning, it's critical because the storm often create rapidly changing hazards such as flood, storm, hues and strong winds. In this project, we used real NOAA storm data to map these danger zones. We converted storm event location to hazard maps and then applied AI search algorithm to compute the safest route from a danger to a safe zone. Our main objective is to project to generate an optimal evacuation path while minimizing exposure to high risk storm areas. We compared two classical search algorithms, UCS and A star, to evaluate which perform better in terms of cost, runtime, and efficiency. Our approach included several steps. First, we collected NOAA storm data and pre-proceed to extract coordinates. Next, we generated a hazard grid and visualized its heat maps and 3D surface. We then implemented a search-based AI agent capable of navigating the grid. Finally, we ran both UCS and A star to compute route and compare their performance. Our deliverables includes the clean storm dataset, hazard visualization, the implementation of UCS and A star, the evacuation route plots, a performance comparison table, and our final project documentation and presentation. We implemented both algorithms from scratch. UCS stand nodes by the lowest cumulative cost and guarantees optimal path but tends to explore more nodes. A star enhance this by adding a heuristic in our case, including distance, which speeds up the search while they guaranteeing optimal result. Both algorithms output the final evacuation path, the number of nodes expanded, and the overall runtime.
Okay, for our output of implementation, we need the optimal evacuation path for both UCS and A-star search, the nodes expanded, the runtime comparison, the visual route plot, and the cost and runtime evaluation table. On our algorithms, so we create the UCS path, the UCS cost, the A-star path, and the A-star cost. And then we also create the UCS runtime and the A-star runtime. Then we create the table between the two, the total, including the total path cost, the path length, the nodes expanded, and the runtime. We'll later further explain these results. Here we have the storm event heat map, 3D surface plot, the hazard grid, the path comparison overlay. We can see that both A-star search and UCS both are identical. Their paths are identical. The past cost evolution graph is also very, very similar. Here we have a bar graph of the top 15 regions where storms are the highest. Okay, for the evaluation summary, when dealing with the path cost, we can see that UCS and A-star search are identical. So we can move to the runtime evaluation, and we can see that A-star is a little bit better than the UCS path runtime. Okay, for the comparison table, we can see that the total path cost for both A-star search and UCS were identical, so they were both optimal when dealing with cost. The path length and nodes expanded were the same, and we can see that the runtime for A-star search was a little bit faster than UCS. To summarize, we used the storm data to successfully model the hazard grid. UCS and A-star search were implemented to compute the optimal paths. While both produced identical routes, the A-star search was more efficient, and the framework can be used in future evacuation plannings with this data. Thank you.